Today's lesson is going to focus on trends in the periodic table. And we're going to look closely at atomic size or atomic radius, ionization energy, and electronegativity. We measure atomic radius in atoms rather than the overall diameter. And the reason for that is that the outer edges of the atom are sometimes not easy to determine based on the newer models of the atom, something we have not talked about yet. The unit is picometer, and it is a very small amount, 10 to the negative 12 meters. So when we report atomic radius, just remember it's radius, not diameter, and 140 picometers might sound a little large to you, but it is in fact not. So on the periodic table, we want to know about these trends as they move across a period, okay, across a row, or down a group, or down a column. So how does atomic radius change across a period? A lot of times students think that it gets bigger because you're putting in more electrons and protons. And in fact, that is not true. It is smaller to the right of the periodic table. And the reason for that is you do have more protons in the nucleus, but when you have more protons, it means you have a greater nuclear charge. Okay, so what that means is that it's more positive inside the nucleus at the end of the period than it would be at the start of the period because you have more protons. If you have more protons, you also have more electrons surrounding that nucleus as you build up valence electrons in the outer energy level. So a higher electrostatic force, this just means electrostatic, the attraction between positive and negative forces, okay? So higher electrostatic force pulls those electrons closer to the nucleus and causes the radius to decrease in size. So here's an example of two atoms that are side by side on the periodic table. Lithium comes first, beryllium comes second. Many people think beryllium should be smaller simply because it's got more electrons, more protons, more neutrons. And in fact, the opposite is true. So here you'll notice our protons are right here. We have 3 protons in lithium, and we have 3 electrons that are being attracted to the nucleus of lithium. If you go over to beryllium, we add in 1 extra proton, right? You might think, oh, big deal, 1 extra proton. Well, it actually is a big deal. And you also have added an extra valence electron that is allowing now the attraction for electrons to happen all over the atom as opposed to only 3 sides. Okay, so when you have more of an attraction that circles the entire atom, it's kind of like a belt, right, that you'd fasten around your waist. It kind of cinches in everything and pulls the atom closer to itself. When we think of atomic radius as we move down the periodic table, so down through a group, it is larger as we move down the group. And this is much easier to understand. As we move down a group, as you can see here in this image, we add on an extra energy level. We know that as every period increases, we've added on an extra energy level with which to put electrons in. So valence electrons in higher energy levels are further away as a result and not bound as tightly to the nucleus. So we say that the electrons are shielded or actually pushed away by other electrons in the inner energy levels. So in here, you get some repulsion happening, okay? And the more electrons that you put around your atom, you get more repulsion from those negative electrons happening. Here's a nice visual of the trend of atomic radius across the periodic table. So you'll notice that it gets larger in size as we move down the groups of the periodic table. And as we move across a period, so we stay within the same row, the atoms get smaller, even though they have more electrons and more protons. But we understand there's a stronger electrostatic force. We are aware that electrons can come and go out of the valence shell of atoms. And when that happens, we form ions. If you have a cation, and recall that a cation is a positively charged ion, those radiuses are going to be smaller than those of their parent atoms. Okay, so here is a neutral sodium atom. Here is a sodium ion who has lost an electron. And when that happens, the reason that the atom becomes smaller is you've lost that outer energy level. So remember, there was one energy level there that had one valence electron. Now that energy level is gone. And also, there are more protons than electrons. So those valence electrons are just more strongly attracted to the nucleus. An anion is a negatively charged electron or element, and we know that our anions are nonmetals, and they have gained an electron. So when they gain an electron, they actually become larger in size. Okay, so anions become larger in size, and the reason is this repulsion that we mentioned earlier. Okay, so an extra electron is going to cause more repulsion within the energy level, and the shielding that's happening with the inner energy levels, and those electrons actually causes your atom, or your ion rather, to become a bit larger in size.